Hey guys, today's video is about model evaluation. We've talked about accuracy, error rate, class imbalance problem, sensitivity, and specificity in the previous videos, so we'll focus on recall and precision today. Just to recap, we don't always rely on the accuracy and error rate, especially when the classes are not balanced. In specific, the model seems to be acceptable given its overall performance, but it's totally useless in a particular class, and that class might be of our interest. That's why we need extra measures, such as sensitivity and specificity, and, in fact, recall and precision are also alternative measures we can use. Let's start with recall. Recall is the percentage of positive data that are correctly classified as positive. It's also a measure of completeness. Here is the confusion matrix. Pause for a few seconds and see if you can infer the formula from the definition of recall. First, the population is the positive data, so it's TP plus Fn. When I say population, I also mean the denominator in the formula. Then, the positive data being classified as positive is called true positive, which is TP. Therefore, the formula is TP divided by P. P is the actual data belonging to the class positive, so it's equal to TP plus Fn. Does this formula look familiar to you? Yes, it's exactly the formula for sensitivity. Recall is just the same as sensitivity. So, there are two terms referring to the same thing, just because recall origins from information engineering domain and sensitivity origins from statistical domain. Alright, let's move on to precision. Precision is the percentage of data classified as positive that are actually positive. It's also a measure of exactness. Again, please try to infer the formula based on the confusion matrix. First, the population is the data classified as positive, so this time we look at the whole positive column, which is TP plus FP. Next, we want to find the actual positive data out of the predicted positive data. In other words, in this specific column, which position is the actual positive? Obviously, it's TP, true positive. Thus, the formula for precision is TP divided by TP plus FP. Alright, let's look at an example. If you remember, we used this example multiple times before, and the accuracy for this model is 0.938. We want to find the recall and the precision, and basically, we just follow the formulas and plug in the numbers. So, recall is TP divided by P, which turns out to be 1/3, and precision is TP divided by TP plus FP, which is 2/5. That is, the completeness of this model is about 1/3, and the exactness is about 0.4. As you might notice, the interest of these two measures is true positive, and true negative is not involved at all. Thus, we use recall and precision when we don't care about true negative. Last, I want to remind you two things. The first one is, in some cases, we may only care about precision alone or recall alone. Here are the formulas. Can you think of the situation when we only care about precision? The most common case is a random advertisement. To illustrate, when we put an advertisement online, we target at people who we believe to be potential customers. What we care about is the percentage of potential customers that literally buy our products and become actual customers. And this is exactly the concept of precision. Next, can you think of the time when we only want to make recall higher? One of the examples is the access control system. In specific, we want to know the percentage of people who have the access that can actually get into the system. In a company, everyone has different permission level to the database, and we want to make sure people who have the permission can actually retrieve the data. That's the concept of recall. On the other hand, we don't need to predict whether a person has permission or not, so we don't really care about precision. Okay, so the second point is that precision and recall are typically trade-off, just like sensitivity and specificity. For instance, when a model classifies all the tuples as positive, we get a confusion matrix like this. This column is 0 because the model doesn't predict any of the data as negative. And the precision for this model is 0.0194. The recall is 1. In other words, out of the predicted positive data, only around 2% are really positive. However, for the actual positive data, all of them are correctly classified. If we only look at one measure, we might be fooled by the number. Consequently, except for the situation when we know we only care about one measure, we should always look at both measures to get a comprehensive idea of the performance of the model. Okay, that's the basic idea of precision and recall. Thank you for watching my video and hope you enjoyed it.